to remember the past and not the future. We can decide the future and not the past. And I think this is fascinating because the distinction between past and future is so dramatic for us that to think that it's just accidental, just how things are arranged, is strongly counterintuitive. And yet, I think it's real.
Welcome to Closer to Truth. I'm speaking with theoretical physicist Carlo Rovelli about his expansive, exhilarating new book, White Holes. The book offers a scientific and poetic understanding of some of the most astounding ideas in astrophysics and cosmology. I absolutely love the book. I learned some too. Welcome, Carlo. It's great to see you again. Congrats on White Holes.
Thank you, Robert. Thank you very much for what you've said, and it's a pleasure to be again with you here.
Before we focus on the science, and we're going to get into quite a bit of depth, let's just explore the poetry for an opener. I appreciate the poetic parallelisms throughout the book about the deepest ideas in physics and cosmology: black holes, white holes, time, irreversibility, often referring to Dante and his guides in the Divine Comedy. It's wonderful to read, but is there a serious, deep message here about the aspirations and quests of the human spirit to discern what we perceive to be ultimate reality?
Maybe yes, or maybe several. One is that I do think that the poetic imagination and the scientific imagination talk to one another. There is a reciprocal inspiring, I would say. Of course, they're very different. The methods are different. Validation is different. But there's a dialogue that goes back and forth. And specifically Dante, I mean, when I was writing this book, going to the horizon of the black hole, going inside, coming out the other side, my Italian education just was screaming inside me, it's the same trip as Dante. So the parallel came natural to me.
Yeah, it really works wonderfully in the book, and it flows, and it's just a terrific read. Let me begin with a brief bio of your magnificent career. Carlo Rovelli is a theoretical physicist who has made significant contributions to the physics of space and time, including loop quantum gravity, which we'll discuss. His books include 7 Brief Lessons on Physics, The Order of Time, and Helgoland. All are international bestsellers translated into more than 50 languages. He has been included among the most influential global thinkers by Foreign Policy and Prospect magazine. So, Carlo, let's begin with part 1 on black holes. Give a brief definition. Most of our audience are very familiar with it, but for those who are not, tell us what it is. And then what I want to do is focus on where I think you have some very special ideas in terms of the inner tunnel and how that works, and what is the singularity and where is that singularity?
Yeah, very good. Thank you. The question, what is a black hole, is not a completely trivial question, because one can give a mathematical definition of a black hole, but I think it would be misleading today because we see black holes in the sky and they are very well described. They're well described by the current mathematics, but I think the best definition today of black hole is those things that we see in the sky. Because if we do that, we are not trapped by our mathematical definition that might confuse us. And we'll come back to that. For instance, a mathematical definition which one finds in books is that a black hole is an event horizon, which is a surface from which things can go inside and never come out forever. And if one gives this definition, one might blind himself or herself from the possibility that on the long future time, things could actually come out. So I would say a black hole is those objects within the sky. We have extraordinary evidence of their existence. There are many, they're all possible sizes. And they are very well described, to some approximation, by Einstein theory. So they were predicted by Einstein theory. And most of those that we see were formed by stars which have stopped burning, and so they don't have the pressure that keep them open. The weight of the star make the star sort of collapse into itself, become smaller and smaller. And what the Einstein theory predicts is that this funny surface form, which is what we call the horizon of the black hole, which is a sort of sphere inside which everything has fallen and things can keep falling, and from which, at least for a while, we don't see anything coming out. And there is an enormous amount of density, so enormous mass in a small region. There's very strong distortion of space and time outside. And all the astrophysical evidence about this object confirms Einstein theory, namely that there is this incredible distortion of the speed of time and the geometry of space in the vicinity of these objects. So that's, I would say, what a black hole is.
Okay,
in the sky, well described by GR.
So just to give a sense of where these are, we find them at the center of, if not every single galaxy. I think we now think that there is a black hole in the center of a galaxy, which gives some sense of galactic formation and such. There are other black holes of different sizes, as you've said. So throughout the universe, we now believe that there are literally billions of them. And also in the early universe, through James Webb Space Telescope, we now see black holes apparently occurring earlier than we thought they should have been due to the collapse of stars. Does that affect the theory at all?
Yes, for sure we haven't seen all the possible black holes that could be out there. We were surprised by finding black holes bigger than we expected, surprised by finding black hole earlier than we expected in the universe. We've seen many black holes with masses of the order bigger than the sun, which are the ones we understand better because we know the cycle of the life of a star, and we know that the star bigger than the sun are likely to become black holes. And we see these huge, colossal black holes in the center of galaxies that you say almost every galaxies have one of these colossal black holes in the center, million times the sun mass or even billions. So there's all this variety of objects out there. Probably, I would say, most likely we haven't seen all of them yet, all kind of black holes yet.
Yeah, indeed. Black holes is probably in one of the areas of cosmology where we've had the most new information. In addition to the expansion of the universe, of course, is probably the area of the greatest knowledge in terms of quantum physics and general relativity and how it all works. So the more varieties, as you say, that we discover, the more tools we have or areas to test our physics. And so it's a remarkable area. So now, look, I want to focus on what I thought was some of the really exciting original aspects of the book. And the first one is this tunnel description, and you have some very nice illustrations in the book. Especially as time goes on, when there's a shrinking of the black hole due to Hawking radiation, that inside the tunnel can still get longer and bigger and infinite.
Yes.
that sounds very counterintuitive.
Yes. Let me say this. In the book, I describe as careful as I can what happened on the horizon itself, near the horizon and just inside the horizon. And the time distortion, because time is slowed down dramatically near the horizon. So I give a careful description of that. And this is just relativity, Einstein theory. And then I describe, if we go in, imagine we approach a black hole, we cross the horizon, we're inside, the geometry inside. And there is a common misunderstanding, quite widespread, which I try to correct. And this is not my original idea. I'm just sort of explaining general relativity a bit better. It's what follows from Einstein theory. It's a common misunderstanding about what is inside. People sometimes have the idea that inside there is something static, like outside, right? It's black hole, nothing happens if unless something falls in new. You can imagine you sit outside the black hole and just wait, and the black hole stays there. And it's a common idea that inside nothing happens also. And if you can go down, you can fall to the center, and in the center there is the so-called singularity, where is the point where general relativity does not work anymore. Now, this picture is wrong because the inside of black hole is not static, is not stationary. So there is no picture of the internal geometry of black holes at some time, at any time, the same. The interior geometry is dynamical, keep changing, keep moving, and the geometry keep moving. And most importantly, the singularity is not down at the center. So the best way of understanding the internal geometry is to think that the inside is very big. So you have the horizon, which is a sphere. You go in, and to your surprise, if you want, the inside is much bigger than you would expect from the size of the sphere, which is of course allowed by general relativity because it allows distortion of space. So this is a huge distortion of space. So in a sphere like this size, inside there is a huge thing which you can describe as a long tube, very, very long tube. Uh, and as time goes on, two things happen. So imagine you go in, it's dynamic, so it changes. One thing is that the tube becomes longer and longer and longer. And in the meanwhile, the angular size of the tube shrinks around you. So you're inside, the tube becomes longer and longer. You never get to down there. Down there, there's still the star that originated the black hole. And this tube shrinks around you, and in a short time, in your clock time there, in a short clock time there, the tube shrinks around you and becomes a singularity. So it becomes, the curvature grows until the point in which it becomes infinite. Or if you want, general relativity is not reliable anymore. You expect something else to happen.
Now, during that process, that the tube gets longer and thinner, if you will. I don't know if these terms are proper.
Yeah, I think it's very good. It's longer and thinner is the right term.
Okay, and you also say that the original star, which was falling into the singularity, in its frame of reference, continues to fall, and so, what is driving that over time? Is it the original singularity is driving that dynamism in the black hole as the tube gets thinner and longer?
So far, there is no singularity at all. This is just classical general relativity. This is exactly the prediction of Einstein equations. What is driving this dynamics is the dynamic of space and time itself. It's like gravitational waves. It's the actual dynamical evolution of the shape of space as described by Einstein equations. So the Einstein equation, Einstein theory, it's a dynamical theory about the shape of space and the shape of space-time. So the star that has fallen is still down there at the bottom, if you want, at the end of this long tube. And the tube itself is shrinking, as you say, become thinner and longer, which means that's a key point. At some point, there is a singularity. Okay, the singularity is where the Einstein theory goes wrong. Now, where is the singularity? The singularity is not down there where there is a star. The singularity is all over. It's wherever you are inside the black hole. At some point, the universe, the space shrinks around you, and you fall, and you find yourself in a singularity. If you want an analogy, imagine you enter in a room, and you're told that somewhere you're going to be squeezed. A black hole is not that there's a corner of the room down there where there is a singularity. Wherever you are in the room is squeezing around you. So you find the singularity in the future of wherever you are, not in a point in space, but in a point in time, so to say.
Yeah, so that's the key idea. The singularity is not at a specific point in space at the center or at the of the black hole horizon. It's a point in time
Correct.
after this event occurs. Now, when you say you reach that singularity, is that a step function, a very fundamental change at that point, or is it it's obviously happening gradually, but is there a fraction of a nanosecond, an attosecond that it actually occurs?
You reach the so-called singularity gradually, but in the following sense. If we just take Einstein theory, which is generically reliable until something goes wrong, the singularity is a point, or if you want, a moment of time. It's the end of the evolution when this tube shrinks and becomes a line. However, this is a point. We expect that when the tube is very thin, Einstein theory is not good anymore, because that's when we expect quantum phenomena comes in. And quantum phenomena are always there, but they're negligible, completely negligible, until the curvature it's very high. So at this point, you expect quantum phenomena to start becoming more and more important, and therefore Einstein theory not be reliable anymore.
And that arguably could be at when something gets to the Planck length or some fundamental aspect of
Yes, that's
space
exactly
time.
that's
That
exactly the case. So if you compute the curvature as time passes and you approach this shrinking, the curvature gets to a Planckian value, and the
we're doing
that's
10 to the
in the
minus minus 43 or 30. What is the Planck length? So we just get a
it's 10 to the in terms of length it's 10 to the minus 33 centimeters, so it's very small, which means in terms of curvature it's very high. It's, imagine a piece of paper rolled to make a cylinder
right.
which is a diameter of 10 to the minus 33 centimeters. Extremely small. It has to curve very much,
Yeah.
and this curvature is what uh, we expect. If anything, if we understand anything about quantum mechanics, we expect that at this point quantum phenomena must come in and be major, dominate.
We talked about the time frame. I'd like to understand the what you call the falling or collapsing of the star as a process into the singularity from two reference frames. One is from the reference frame of the star itself, and the second is from our external reference frame. What would the times be in each of those cases for from the initial collapse until the final singularity?
Okay, good question. I can answer this question only in part. I will be able to answer this question much better after we go to the white hole
Okay,
picture.
okay. We're going to get to
But I
that.
can say the following. I can say the following. Take a biggest black hole that we know, that we have seen, say billion solar masses, and imagine that we take a starship, we go there, we cross the horizon, and we go in. Okay. Now we are inside. The space is shrinking around us, and the time it takes to close around us is of the order of hours or maximum days. So we don't have much time there to do many things. So the inside of black hole, if you want, is huge in space, but is short in time. Very rapidly you get to this quantum phase. Now, for the moment, I cannot answer what happened in the mean, how much time is corresponds outside, because they are disconnected. I cannot from the inside send a signal and say, "Hey, I'm falling in the singularity. Now I'm in." Quantum effects are coming, because if I send this signal, it's not going to go out. So I can't compare for the moment, but I will soon.
Okay, very good. So we now want to move to the transitional ideas from black holes to white holes.
Yes.
And one of the concepts, there are several concepts that you introduce in black holes. One is the concept of a bounce as you
Yeah.
get to this singularity, what that means. The second, we've sort of already covered the granular nature of the space-time
Yeah.
environment, as the contraction squeezes the tube inside the black hole before the singularity. So just introduce those concepts, which I think lead directly to part two, which is on white holes.
Yeah, and this to introduce this concept, the important thing to say is now we are jumping out of classical generativity of Einstein theory. So to know what happened next, we need a theory of quantum gravity. We need to know how quantum effects uh, uh, affect space-time. And there's no consensus theory of quantum gravity. There are, because there are some theories out there, but there are no experiments so far or no observation that supports them. But there are some theories. So we can use these theories, and the theory on which I've worked a lot during my life, as you mentioned, is loop quantum gravity, which arguably it's most developed or among the most developed tentative theories of quantum gravity. So we can use it and have an educated guess of what happened next. And what the theory tell us, it's two things. One is that there is a quantization of space in the sense of quanta, grains, very similar to the quantization of light, which is the quantum phenomena that the light that we see has a granular structure. We can think of it as made by photons. More precisely, when it arrives on a screen, light arrives in dots, in individual dots. So these are the individual grain of light. And we know the size of this grain for even frequency of light. Now, similarly, what the quantum theory of gravity, what loop quantum gravity predicts, is that the continuous space of general relativity also, it's granular, exactly in a very similar manner. And we can predict the size of its quanta of space, its grain of space, which means that you cannot go smaller than that. These are the minimal size sort of space. There's no space smaller than that, which of course tell us that this tube cannot shrink more than something because there is nothing smaller than something. So something must happen. The second defining feature, I would say, of quantum mechanics is probability. Namely, things don't happen according to a deterministic equation, but happen probabilistically. And the best way of thinking about this, I think, is the old way of Niels Bohr in terms of quantum jumps or quantum leaps. The best way of understanding how light, the photons, is emitted by an atom is that the electron on an atom is some orbits. These orbits are quantized, again, discreteness. And the electron jumps from one orbit to another and emits a photon. That was Niels Bohr's original picture of quantum mechanics. So what quantum mechanics predicts is the probability for these jumps to happen. And it's the core of quantum mechanics. Quantum mechanics is about what's the probability of jumping from here to there. And essentially, it doesn't tell us what happened in between. In between, there's a wave, there's a superposition. There are funny things that we philosophers like to debate, but the strong aspect, the clear aspect of quantum mechanics is that given some initial condition, tells you, well, there's a probability of jumping there. And this is what, these two ideas is what allow us to compute and have an intuition of what happens at the singularity. Because the discreteness block the contraction, the shrinking, and then there is a probability of a quantum jump into something else,
which we call tunneling in other contexts.
Yes, the two defining and most important aspect of quantum theory that comes in here are granularity and the quantum leaps, probability. Granularity is it's clearly shown, for instance, by the fact that light is made by photons. There's a granular discreteness, quantized aspect of quantum things. And once you apply this to generativity, namely to space and time, you obtain the key result of loop quantum gravity, which is space itself is granular. So you have a minimal size of space, which means that the black hole cannot shrink, the tube cannot shrink more than this minimal size. And the second, the quantum leaps, it's the fact that in quantum mechanics you predict probabilities, and you can jump from one classical solution to another classical solution, to one classical trajectory to another classical trajectory, like in Niels Bohr quantum leaps orbits of electrons. And these two features of quantum mechanics are what allows us to have a good guess of what happens instead of the singularity
Okay,
indicated by GR.
those are critically important. And the quantum leap, I love the way you describe it in the book. There's really nothing in the middle. It's not like there's a process in the middle. It just goes from one to the other in some bizarre, strange way to our macroscopic intuitions. And we often have heard the word tunneling, that there's a tunneling between the two, but the process itself is mysterious or instantaneous in some strange way.
That's correct. And this is a mystery of quantum mechanics in general. So this tunneling effect, like a particle that can go through a wall, always have this strange feature. We don't have an intuition about that. But here now, it's particularly mysterious because what is tunneling is not a particle from one position to another. It's space itself, space-time itself, that goes from one configuration to a different configuration.
Okay, so that's the perfect place to now introduce some definitions of white holes. I like, as you put it, in a black hole, you can enter, material can enter, but nothing can exit, not even light. And in a white hole, precisely the opposite. You can exit, things can exit. We'll talk about information exiting, but nothing can enter. And that you say that black holes don't need another solution for Einstein's equation. It's the same solution. It's just reversed in time. So give us some color on how all that works.
Yes, white holes are not definitely not an invention of mine or my colleagues. Are a solution of Einstein equations or predictions of general relativity, like black holes. For a long time, black holes were just something that general relativity allows to happen. And white holes is also something that general relativity allows to happen. And in fact, as you say, they are almost the same as black hole in time reversed. Now, time reversed is not any particular mysterious sense. If you think of a ball falling toward the floor, that's a trajectory permitted by classical mechanics. And if you think of a ball bouncing up, it's sort of the same trajectory reversed in time. Like if you take a movie and project the movie backward. So in the same sense, a white hole is like a black hole of which you take a movie and you project the movie back in time. So everything happens backward. And it is a prediction of general relativity. For a long time, people didn't believe that black holes could actually exist in the universe. Now the question is, could white hole exist in the universe?
Yeah, and this is a fundamental question. You're obviously a great promoter of the theoretical concept of white holes, which is a fascinating probe of reality, whether they exist or not, and you're agnostic on whether they're real, and that's just good science. I think it's fascinating that you state, and it took me a little time to feel comfortable with it, that a white hole can be indistinguishable from a black hole. They both have material gravity works the same, and that from the outside, it might be difficult, if not impossible, to discern the difference.
Yes, this is very tricky. In fact, it's just a general relativity fact, and it took us quite some time to get our mind around. I have a few pages in the book in which I go slowly toward showing how this is possible. What distinguishes a black hole from a white hole is what happened before and after, in a sense. So you have a collapsing star, there's no black hole, and it can form, and now there's a black hole. And a white hole is something that at some point the star can come out, and then there's no white hole. So there's not the same thing because they behave in this different way. But as long as nothing goes in and goes out, if you just sit near a black hole or sit near a white hole for a while, you cannot distinguish the two. And that's quite surprising. One way of realizing that is that we say that a black hole is something you can enter and not exit. That's true. But if you sit near a black hole, you don't see things entering because you see things slowing down and approaching the black hole and never entering. The reason being that the light emitted by something takes longer and longer to come out. So if I go near a black hole, near the horizon, I send you a message, you receive it today, and then tomorrow I send you another message, and you receive it in a month. And then I send you another message just before entering, and you receive it in 1 year. And just a moment before entering, I send you another message, you receive it in 100 years. So while you wait, you always see me approaching and never coming in. This is a funny distortion of time of general relativity.
And that's for a black hole.
That's for a black hole. But you
A
see,
normal black hole. Yeah.
a normal black hole,
yeah.
which means we don't see things actually entering a black hole. Okay. Things do enter. If you go there, you can enter. But if you're at the distance, you don't see anything enter. So what you actually see is neither things coming in nor coming out, neither from a black hole nor from a white hole. That's why they look the same from the outside.
Mm-hmm.
But if you go there, it's completely different. So a black hole, if you fall to a black hole, you just go in. If you fall toward a white hole, okay, you clash against the matter which is going to come out at some point before getting in.
Yeah. Okay. We'll get into that particularly as we go into part 3. But I just want to take a brief aside and talk about a meeting that occurred that you focus on when you were 2 years old between Roger Penrose and David Finkelstein, which I took note of because both are contributors to Closer to Truth, and we've had them on, and people can see their video. So why was that so important in this whole understanding of black holes and eventual white holes?
Yes, I'm happy to talk of them because they're two people very dear to me as effectively, but also fundamental for my science, and fundamental, I would say, for the science of black holes in general. Roger Penrose got a Nobel Prize recently for having understood a lot about the mathematics of black holes. But he, when he was a student, he was interested in else. He was not interested in general relativity. He was interested about things related to quantum mechanics. David Finkelstein, is the person who actually understood what happened at the horizon. Until him, people thought more or less what Einstein thought, namely that the universe stops at the horizon. There's nothing on the other side. Okay, which is a mistake, and is a mistake that many of my colleagues still do, by the way. Finkelstein understood through a simple calculation that I give to my student in the class, that if you fall toward a black hole, from the outside people don't see you entering, but you do enter. You do enter and you go the other side, and you can predict what you see on the other side. And when he understood that was the 50s. In fact, I was 2 years old. He went to London and gave a talk. And younger Roger Penrose came down from Oxford, I believe, to London, and was very fascinated by this talk. And the two started talking to one another. And Roger Penrose got fascinated by general relativity, so he basically switched and got into general relativity, fascinated by David Finkelstein. David Finkelstein was fascinated by what Roger Penrose was doing with quantum, so started developing some idea about quantum and gravity, which were very influential also in the physics that I've done. So they two swapped their interest, so to say, and out of that came the Nobel Prize to Roger, and a lot of quantum gravity ideas, which are informing the kind of science I'm telling you about.
Yeah, and both that was a formative. Both ideas helped you very much in forming your ideas on
On loop quantum gravity, yes.
your quantum gravity, and then black holes, and now white holes.
So the key point here, I don't know if this is the right point too, is that uh, the the open questions was what happened at the end of this black hole evolution.
Yeah.
And as long as white hole are concerned, the open question is that how can a white hole can be born? Uh, from white hole things can come out. Where do they come from? And the key idea of black to white transition is exactly that the death of a black hole is is what makes a white hole be born. So at the end of the shrinking of the tube, this quantum jumps takes us into a white hole, and everything comes back, so to say. That's the core of the theory.
And so that's the bounce, so to speak. That
That's
the
bounce.
bounce is the conversion of a black hole into a white hole when it reaches the Planck limit as defined by loop quantum gravity.
Exactly. Exactly. There's this bounce, which is a quantum jump, is a tunneling, if you want, which goes from a classical solution of Einstein equation to another classical solution of Einstein equation.
Mm-hmm.
And we know that quantum mechanics allows this transition. So there are some computation uh, that have been done that give the probability for this to happen. And we see that there is a high probability. This is so the more you approach the singularity, the more probability this happen becomes high.
Mm-hmm.
So here is the hypothesis, because of course we're not sure about that, right? This is what the theory predicts. There's no observation so far that confirms it. The hypothesis is that inside the black hole, uh, arriving at the singularity in the future, you jumped into a white hole, and then you're in a white hole, and everything that was inside now can come out.
Mm-hmm. And as we'll see, this is a solution, maybe not the right solution, to the information paradox on the horizon, which is a major focal point. And
That's correct.
your solution seems very elegant, which doesn't necessarily mean it's correct, of course. But once again, at that bounce, it's nonsensical to ask what happens in that bounce, how that happens. That's just the brute fact of tunneling or the quantum leap.
Yes, and it's in a sense the most fascinating things, because here we're really going to the core of quantum gravity, right? Quantum gravity, it's a way of thinking reality where you don't need things to happen in space and in time.
Mm-hmm.
You're jumping from one space-time to another space-time through quantum probability, so to say.
Is it in principle possible to get experimental or observational data to support any of this?
Yeah, of course. It could even be practically possible. So there are two directions. One is direct detection of the resulting white hole. So this resulting black hole is small because they happen when the black hole has the jump happens when the black hole has become sufficiently small for this to happen. Because when the black hole evaporate through Hawking evaporation, become very small. At this point, you're deep into a quantum gravity regime. So from the outside, this is when you see things happen, right? At the end of the evaporation. So the white hole are small, and loop quantum gravity gives indication that they are stable or semi-stable. They can live very long time. So the prediction here is very precise. There is a semi-stable particle object at a given mass that we can compute, which is of the order of the Planck mass. Planck mass is not very small. It's a fraction of a microgram. So it's a mass of a hair, roughly. So the prediction is that there could be in the universe a lot of little things, the mass of a hair, floating around that have no charge, they don't interact, strong interaction, weak interaction, just gravitationally, and they float around. So this could be detected. And we're working on how to detect these things. The technology seems not too far from the possibility of detecting these things using some quantum detectors. And so the best would be to see these things, see these Planck mass things, right? If this a Planck mass is almost clearly a quantum gravitational thing, because it's right the scale of quantum gravity. Now, the possibility which I find extremely fascinating, and it's really what motivates the interest in all that, is that a lot of this uh, little Planck math things could be the mysterious dark matter
Ah,
that astronomers see in the sky.
mm,
So, if in the early universe, near the Big Bang or before the Big Bang, who knows, small black holes have finished evaporation, they're transformed into white hole. There could be all these little things around, and if so, there should be some matter which is dark, which only interact gravitationally. And look, there is. It's called dark matter.
mhm.
So it's tempting to say, aha, these are these things. Of course, we don't know. Once again,
Carl, that's the perfect segue into part three, perhaps the most fascinating part of the book, time and irreversibility, when we begin talking about the possibility of these white holes. Could they be dark matter? But let's get into these white holes, because you caution us in terms of thinking as the black hole shrinks and the horizon shrinks and it becomes microscopic, does not mean that the interior of the black hole becomes smaller. In fact, I think you say even the interior can continuously become larger even as the horizon shrinks to this very small size, and that all the information, which we want to define what that means in terms of matter or literal information, is maintained in there. So, I mean, this boggles the imagination. I just want to ask, is what I said a correct understanding of the book?
yes, is correct. And I think there is a common misunderstanding today in theoretical physics that small things cannot contain large information, which is only true as long as uh, the horizon is eternal, if you want, as long as a black hole remains a black hole. But a black hole can becomes white hole, so whatever is inside can come out. And as you said, this is general relativity. A small horizon does not mean a small inside. A small horizon, so a small black hole, could have a huge space inside. That's just classical GR that shows that. And inside there could be an enormous amount of information. Now, information is not something mysterious. Is that if you know exactly what inside there and what is outside, you can reconstruct what was in the past. That's the meaning of information.
Yes.
So if you know the past, you can predict the future. Principle, if you know the future, you should be able to reconstruct the past. If you could know everything, okay. But to reconstruct the past, what is outside is not sufficient. You also need the inside, because some information has gone inside. And inside the black hole is an enormous amount of space. And because of that, there is a container for all possible information that you want.
And is there a limit of the internal size as the external size is finite and very small, or
Yes, it depends on the original mass of the star
oh, okay,
that fell in.
okay,
So you start from a star, which is a certain mass. You evolve for a certain time, outside time, which is the time it evaporates. And from the time and the original mass, you have a finite volume inside. So inside the volume is not infinite. It's finite. It's bigger if the original star was larger.
right. And as you assign information, you can't assign information to anything smaller than the Planck length, right?
Absolutely. Absolutely.
Okay, so the internal extreme curvature is what's causing the amount of space to be so large, so that each Planck length could or larger than that can contain a single bit of information
Yes.
related to what the original star was.
Yes. Very good, Robert. You're pointing to something very interesting here. Remember, there is the inside shrinks in one dimension, in two dimensions, but one dimension becomes longer and longer.
Yeah.
So it's shrinking and longer, but it's becoming longer faster than it shrinks. So the volume is increasing. It's not becoming small.
Yeah, amazing way of thinking about it, and there is definitely a coherence to it, which is very, very exciting to see. What are the implications of this in terms of the expelling of the information? Is this an automatic process like Hawking radiation would be with a black hole, or is there some external factors which affect it?
No, we've been computing what could be the emitted radiation from the white hole, uh, can be computed quite easily from the constraint of all the game. I'm not going to go in technicalities. Essentially, a white hole, whatever is inside, whatever field you have inside, electromagnetic field, fermion field, whatever excitation has to go out because it's a white hole. So slowly everything has to leak out. And when completely the energy has been thrown out, then the white hole disappears.
Okay.
Exactly like the black hole doesn't exist in the past
Mm.
before things come in. So we are back to known physics, right? The unknown physics is only the jump.
Mm.
That's a strength of the of this scenario, if you want. What happened before, after, is just solid physics that we control. The part where you have to have quantum gravity, there is just a jump.
Mm. And you make the point that the expelling of the information from a white hole takes much longer than the Hawking radiation in a black hole.
Yes, yes, this is a constraint because one can estimate the amount of information which is inside, uh, which is large. Essentially, because for those who understand technically the things, there's an entanglement between the inside and the outside. Outside is not a pure state, so it's missing information which is inside. So we can estimate the information inside, but there's a very little energy because the white hole is small.
Mm.
So you need to have a lot of information with little energy. This is possible. It's perfectly possible because if you have a lot of photons, low energy, you have a lot of information. Each photon can be, say, polarized up and down.
Sure, sure.
And you can make the energy as small as you want and have as much information you want. But low energy means long wavelength and low frequency, so long time. So then you need a long time for everything to come out.
Yeah, and just to be simple, because the black hole can be huge, it can be the size of our solar system for a large black hole. There's a lot of area in that, and that same information would be in a white hole, but now the mass of a hair grain.
Exactly.
And so that same information has much less surface area to escape from. So it'll be many orders of magnitude of more time to occur.
Correct. Exactly, Robert.
Okay, now you then make the fascinating jump, and I don't think it's a quantum jump. I think there's some logic to it, where you now describe the difference between the past and the future. Yes. That we can know the past, speaking macroscopically, but not the future. But we can choose the future, but we cannot choose the past. Now, these obvious things, as we think about time, you then have derived from this whole theory.
Yes, the connection is this: the bounce by itself from black to white is time symmetric, right? It's like bounce. It's a white hole is time reversal of the black hole. And the time distortion of the process is colossal. Now I can answer a question you asked me before. The time outside and the time inside. So if you have a star with a big mass, it takes forever to collapse. Mm-hmm. And then it jumps and it takes forever to finish. Okay. So the time process can last, if the star was big, billions of years. But if you jump in, okay, you go through the bounds, assuming you survive, you come out very fast and you're immediately in the future. So inside is half an hour, outside is many billions of years, mm-hmm. Which is mind-blowing. The process is sort of a shortcut to the future. Mm. So time here seems to be completely deformed colossally, and that's a surprising thing. The evolution, the thermodynamical evolution, always going one direction. So the entire process is dissipative in the sense of the second principle of the dynamic. Entropy keeps growing. It's not coming back. And this is marvelous. So the process has a time direction and is given by entropy. And then in the book, I ask, wait a minute, where does the time direction come from?
Yes.
In the phenomena that to us are more time directed, like what you mentioned, right? We remember the future, we don't remember the past. We remember the past, we don't remember the future. We can decide what to do, where to go for dinner tomorrow, but we cannot decide where to go to dinner yesterday. There's nothing to do. So there seems to be something dramatically different between past and future. And yet, physics tells us that that's not the case. It's only entropy, which means how things are arranged. It's only accidental. So I go through this careful description of how come that just because of the way things are, just before dissipation, just because the energy is concentrated or diluted, that's a source of the fact that we remember the past and not the future. We can decide the future and not the past. And I think this is fascinating because the distinction between past and future is so dramatic for us that to think that it's just accidental, just how things are arranged, is strongly counterintuitive, and yet I think it's real.
And you use the concept of disequilibrium as a mechanism to be able to intuit this better.
Yes, because if you take a physical system, and you wait long enough with some conditions, it goes to equilibrium. And when is at equilibrium, okay, all temperature are the same, everything equilibrates. Then you don't see distinction from the past and the future. You only see distinction of the past and the future in the equilibration. Mm-hmm. And so therefore, at some point, something is out of equilibrium, and that's what generates a direction of time. The flowing out of it is the direction of time.
Carlo, this has been absolutely terrific. I can go on for all day. The book is wonderful. It's an enjoyable read. It's a quick read, but it is so engaging. White Holes, I recommend it for everybody. It is an enriching experience in many respects. So many thanks. I loved our conversations. Viewers can watch dozens of TV episodes and hundreds of exclusive videos on cosmology and fundamental physics, including certainly many with Carlo Rovelli on the Closer to Truth website and Closer to Truth YouTube channel. Also, other people we've mentioned, Roger Penrose, David Finkelstein, and others, Lee Smolin, Ed Witten, Stephen Weinberg, Kip Thorne, all of these on the Closer to Truth website and Closer to Truth YouTube channel. Carlo, once again, terrific. Great to see you. Congrats with the book.
Thank you very much, Robert. That was great. I really liked it.
Thanks everyone for watching. Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.